Okay, back for another tutorial. This one is about stationary points or turning points. Let's jump right in. Stationary points are points on a curve where the gradient is 0. That is, at a stationary point, the gradient function dy dx, the gradient is 0, and therefore you equate the gradient function dy dx to 0. You would remember in the last tutorial, we were looking at finding the coordinates of the point or points on a curve where the gradient has a specified value. And I think the last example that I did was one in which I actually defined the coordinates of the point or points where the gradient is 0. Well, effectively, in that example, we were finding a stationary point. I just didn't call it a stationary point at that time. Well, now you know the specific name for points and curves where the gradient is 0. Right? They're called stationary points. Sometimes they're called turning points. All right, so let's jump right in. Here's the first example. Find a stationary point or points on the following curves. Remember, a stationary point is a point in a curve where the gradient is 0. So if we can find the gradient function, equate it to 0, solve for x, plug in back and solve for y, that's our stationary point. Let's go. Example number 1. I'm doing a bunch of nonsense here. All right, yes. Gradient function in this case, dy dx, is equal to 3x squared minus 3 at a stationary point. SP is my shorthand for stationary point. I'm going to equate dy dx to 0. Equate the gradient function to the specific value of gradient, which is 0. And therefore, 3x squared minus 3 is equal to 0. X squared is equal to 1. X is equal to plus or minus the square root of 1. X is equal to plus or minus 1. There are two stationary points in this curve. We'll simply take each x value, plug it into the original equation, and find the corresponding y coordinate. When x is equal to 1, y is equal to 1 cubed minus 3 times 1. That looks like a minus 2, I think. 1 minus 3 is minus 2. When x is equal to minus 1, y is equal to minus 1 cubed minus 3 times minus 1. That'll be a plus 3 at the end and a minus 1 in front. It looks like 2. So there are two stationary points in this curve. Two stationary points. The coordinates are 1 and minus 2. And the other one has coordinates minus 1 and 2. Well, that's not so difficult. Let's try the next example. What do I need to do here? Yes, here's the next example. Find the coordinates of the stationary point or points on this curve. Again, up to this point, we've only learned one rule for differentiating a function. So we have to first convert this into a standardized polynomial before we can differentiate. In the next tutorial, we're going to learn a bunch of other rules for differentiation, so not to worry. One good way to do this is one good way to make this into standard polynomial is to split it into two terms. This becomes x squared upon 2x plus 9 upon 2x. Y is equal to, okay, the first part is obviously a half x, right? One of the x's in the numerator will cancel with one in the denominator. Fraction in front is a half. The second one is 9 halves is the fraction. And we'll take the x from the bottom here and throw it up into the numerator. This becomes x to the minus 1. And there, you have your function in the standard form of a polynomial. dy dx, in this case, is equal to a half. And then this becomes minus 9 halves x to the minus 2. You're going to tidy this up a bit. 1 over 2 minus 9 upon 2x squared. Don't forget your indices. LCM here. dy dx is equal to 2x squared. Right, 2x squared there minus 9. Yeah, that looks good. Okay, now remember we're finding the stationary point or points in this curve. So at a stationary point, you must equate the gradient function dy dx must be 0. The gradient of the curve or the gradient of a curve at a stationary point is 0. And therefore we can say x squared minus 9 upon 2x squared is equal to 0. Cross multiply there, I get x squared minus 9 is equal to 0. X is plus or minus 3. Don't forget when you square root, it's plus and minus. I just found the x coordinates of my stationary points. I need to find the corresponding y coordinates. So let me write back the y function. Y is equal to x squared plus 9 all upon 2x. When x is equal to 3, y is equal to 3 squared plus 9 upon 2x. Upon 2 times 3, man. What's wrong with you? X is 3. 18 upon 6, that looks like a positive 3. And when x is equal to minus 3, y is equal to minus 3 squared plus 9 upon 2 times minus 3. I still have 18 in my numerator upon minus 6, and that's a minus 3. So my stationary points, two stationary points here again. And their coordinates are 3 and 3. Minus 3 and minus 3. So the concept of finding a stationary point, it's not difficult. I'll reiterate one more time. To find the stationary point on a curve, or to find these stationary points on a curve, you find the gradient function dy dx and you equate that gradient function to 0. At any stationary point, dy dx is 0. Okay. Now, the fact that you know where your stationary points are doesn't really tell you what type of stationary points you have. Stationary points come in 3 main types, as you'll see there on that graph. Stationary points come as maximum stationary points, minimum stationary points, and points of inflection. Maximum stationary point is the one on top there. I missed another maximum. There's a maximum there as well. That's also a maximum stationary point. Maximum stationary point looks similar to the way a curve would turn. To the way, you remember your parabolas? You call it your maximum minimum parabolas. Okay. Right. And at your maximum stationary point, that's how your curve turns. The gradient goes from a positive gradient to zero gradient at the stationary point itself, and then to a negative gradient on the other side. Positive, zero, negative. For a minimum stationary point, the gradient goes from negative to zero to positive, like that. For a point of inflection, the gradient will go from positive to zero and back to positive, or from negative to zero back to negative, right there, or right there. And the question is, how do you decide what type of stationary point you have? In most cases, if you notice in the two examples that we just did, we didn't draw a graph, right? In the first example, 1 and minus 2 and minus 1 and 2, those were two stationary points. How do we know what kind of stationary points we have there? Second example as well, 3 and 3, minus 3 and minus 3. I don't know what type of stationary points they are. Is there a way we can test to see what type of stationary point we have? And the answer is a resounding yes. There is a test. In fact, there's more than one test that you can carry out to test your stationary point, to determine what type of stationary point you have. Okay, the first test we're going to look at is referred to as the second derivative test. Let that soak in for a minute. Second derivative test. Now, so far when we were differentiating, all we've done with a function is to differentiate it once. That first time we differentiate, we refer to the result many different ways. dy dx, the gradient function. But you can also call it your first derivative. So let's look at that function that we have there. Y is equal to 5x cubed plus 2x squared minus 5x plus 6. If we differentiate that once to get dy dx, the result there is what? 15x squared plus 4x minus 5. Well, who says you couldn't differentiate that first derivative? Who said you couldn't differentiate that to get another function? When you differentiate your first derivative, you end up with what's called your second derivative. And the notation for it is as shown there, d squared y upon dx squared. Well, you differentiate it in the same way as you would have differentiated the first time. 15 twos, that would be 30x plus 4. And why can't I get a third derivative? There's no reason I can't differentiate a third time. D cubed y upon dx cubed would just be 30. And if I really want this whole thing to disappear, I can actually get a fourth derivative. Here, a fourth derivative. D fourth y upon dx to the fourth would be 0. When you differentiate a constant there, you get 0. In terms of notation, you should become familiar with this notation as well. In many cases, you don't call your function y. Almost everything we've done so far, we've called the function y. Sometimes, as you know, you call your function f of x. Well, in terms of notation, give me a second, let me rearrange something here. Yes, in terms of notation, you might want to call your function f of x. And what's the notation that you didn't call it y? So how would you determine what your derivatives are? What would you call your derivatives? Well, the first time you differentiate, if you look at the notation there, I'll rub it out and do it over. There. Your first derivative you refer to it as f prime of x. That's not f inverse, that's f prime. F prime means you've differentiated once. So the result is your 15x squared plus 4x minus 5. Your second derivative is f double prime of x. You refer to it as double prime, 2 primes, there. That would be 15 2's 30x plus 4. Your third derivative, f triple prime of x, would be 30, and your fourth derivative, f quadruple prime, prime, you're differentiating 4 times, would be 0. Right, so it's just different notation, but you're effectively doing the same thing. dy dx, d squared y dx squared, and so on. The first and second derivative. F prime of x, f double prime of x. First and second derivative. Okay. We are interested in only the second derivative to test the nature of our stationary points. So this one, this guy, is the important one, right there, or right there. Just the second derivative. Your next heading says the second derivative test that's used to determine the nature of a stationary point. And here it is. If at a stationary point you find that the second derivative is greater than 0, or positive, that implies that the stationary point is a minimum stationary point. If at a stationary point the second derivative is less than 0, which is negative, that means that the stationary point is a maximum stationary point. If at a stationary point the second derivative is 0, the second derivative test will fail to determine the nature of your stationary point. All right, the second derivative test fails. On its own, it wouldn't be able to tell you what type of stationary point you have. Okay, so let's jump right in. I have 2 examples there. I might do one and just give you the second one to do on your own. Let's see. Find the stationary point or points on each of the following curves and investigate their nature. So let's run the first one. Okay, so to find your stationary point, you first find your gradient function, dy dx. Let's go. Dy dx, in this case, is equal to 12x squared plus 6x minus 6. Double check that there. 4 3 is 12x squared, 6x minus 6. We know that at a stationary point, dy dx, the gradient function must be equated to 0, and therefore 12x squared plus 6x minus 6 must be equal to 0. We can tidy that up a little bit, probably by dividing through it by 6, I think. You'll get 2x squared plus x minus 6 is equal to 0. Now we got to solve that for x. Obviously, we're going to end up with 2 different values of x. That's a quadratic function for the second derivative that you equated to 0. Oops, I really messed this up. I'm dividing throughout by 6. So that's 2x squared plus x minus 1. Can I factorize that? I'm looking for whatever I'm looking for. Minus 1 when I add in 2 and I multiply. 2 and minus 1. I don't know, 2x squared plus 2x minus x minus 1. This is 2x into x plus 1 minus 1 into x plus 1 equals 0. 2x minus 1 times x plus 1 is 0. Squared 2x minus x is x minus 1. Yes, I think I'm right. From which I'll get x is equal to a half and x is equal to minus 1. Okay. I need to now use both values of x, plug it back into the original equation to find the corresponding y coordinate. When x is a half, y is equal to 4 times a half cubed plus 3 times the half squared minus 6 times a half minus 1. Lord knows. This is 8 for 8, that's a half. All right, that's not too bad. This is 3/4 minus 3 minus 1. That's minus 4. A half is 2/4. 5/4 minus 16/4 minus 11/4. I think. Again, y'all double check my numbers. I'll double check it here again myself, but y'all can still check it after me. Minus 4, which is minus 16/4. A half is 2/4, and 3/4 is 5/4. 5/4 minus 16/4 is minus 11/4. I think I'm right. And the other one is when x is minus 1, the corresponding y coordinate would be 4 times minus 1 cubed plus 3 times minus 1 squared minus 6 times minus 1 minus 1. This looks like a minus 4 plus 3 plus 6 minus 1. 9 minus 5 is 4, I think. Minus 1 minus 2, 6 minus 2 is 4. That looks good. So my two stationary points are, or have coordinates, a half and minus 11/4, and the other one would be minus 1 and 4. Good. At this point, I know I have two stationary points. However, I do not know the nature of these stationary points. If you look at the question, it says, find the stationary points on each of the following curves and investigate their nature. That means tell me if I have a maximum stationary point here, minimum, or point of inflection. Same here, maximum, minimum, or point of inflection. Well, we just introduced the second derivative test somewhere up here. You find the second derivative. It will, in many cases, not in all cases, in many cases it will depend on x. Sometimes the second derivative is a constant on its own. It has a numerical value all on its own. But you simply follow the test. Whatever value the second derivative ends up being, whether it's positive, negative, or 0. All right. In the case of positive or negative, you'll know what type of stationary point you have. In the case if the second derivative is 0, well, you have to do some further work. So let's see if we can find the second derivative here. Let me write back. Y was 4x cubed plus 3x squared minus 6x minus 1. dy dx, the first derivative, was 12x squared plus 6x minus 6. The second derivative, which will be written as d squared y upon dx squared, is equal to 24x plus 6 right there. The second derivative depends on x as well. So what you'll do, you'll take the x coordinate of each stationary point and plug it into the second derivative. So let's look at the first stationary point, where the coordinates are 1/2 and minus 11/4. At this point, d squared y upon dx squared is equal to 24 times the x coordinate of the stationary point, which is 1/2, plus 6. That's 12 and 6, that's 18. That's a positive number. That number is greater than 0. So guess what? According to the test, when the second derivative is greater than 0, you have a minimum stationary point. So since at 1/2 and minus 11/4, d squared y upon dx squared is greater than 0, it implies that this stationary point is a minimum stationary point. Let's check the other one. At minus 1, 4, d squared y upon dx squared is equal to 24 times minus 1 plus 6. That's minus 18. That number is less than 0. That number is negative. What's my conclusion? Since at this other stationary point, d squared y upon dx squared is less than 0, that implies that this stationary point is a maximum stationary point. Okay, so 1/2 minus 11/4 is minimum, and minus 1 and 4 is maximum. Each stationary point and the nature of the stationary point. There, I've answered that question. I'm going to leave this other one for you to do. I'm going to pick it up in the next tutorial. So I'm going to end this tutorial right here. What I want you to do is this problem here. Just this one. You know what? Let me do it. I'll do it. This is the next one in line. I'll do it. I'll continue this tutorial. Sorry. Good. Same instructions. Find the stationary points on this curve and investigate their nature. So let's go. dy dx is equal to 3 fourths 12x cubed minus 24x squared plus 12x. We know that at a stationary point, dy dx must be equal to 0. And therefore, 12x cubed, minus 24x squared plus 12 must be equal to 0, plus 12x. I can tidy this up a bit by dividing through it by 12, I think. So this becomes x cubed minus 2x squared plus x. X cubed minus 2x squared plus 12 plus what am I doing? X cubed minus 2x squared plus x is equal to 0. I can factor out an x from that into x squared minus 2x plus 1 equals 0. You do the work in between to show that that quadratic portion can be written as x minus 1 times x minus 1 equals 0. So what do we have? We end up with two values for x, really. The second value simply repeats. Either x is equal to 0 or x is equal to 1. The 1 is repeated, but it's only one extra value. Okay, now that we have the x coordinates for our stationary points, we know what to do. Take each x coordinate, plug it back into the original function. So when x is equal to 0, clearly you can see into the y function there, everything goes to 0 except the minus 3. So 0 and minus 3, that's one stationary point. And when x is equal to 1, y is equal to 3 times 1 to the 4th minus 8 times 1 cubed plus 6 times 1 squared minus 3. Let me see, what's this value? Y would be equal to, that's 3 minus 8 plus 6 minus 3. I think. Let's see, 3 minus 8. That's minus 5 plus 6, that's 1. 1 minus 2. Minus 2. So the coordinates there are 1 and minus 2. At this point, I know I have, two stationary points. One stationary point has coordinates 0 and minus 3. And the other one has coordinates 1 and minus 2. I need to investigate what type of stationary points I have. So I'll go back up to the original first derivative right there and differentiate that to get the second derivative. D squared y upon dx squared is equal to, let's see, 12 3s 36 x squared minus 48 x 12 24 2 is 48 plus 12. If you look at the second derivative, it depends on x, so I have to check the x coordinate at each of those points, at each of those stationary points, to determine what type of stationary point I have. So let's look at the first one. At the stationary point 0 and minus 3, if I plug the x coordinate into the second derivative, d squared y upon dx squared, I will get 36 times, oh, this is almost by observation, right? These two terms would go to 0. And you're just left with 12 for the second derivative. 12, that's a number that's greater than 0. Conclusion, since at zero minus 3, d squared y upon dx squared is greater than 0. It implies that 0 minus 3 is a minimum stationary point. Let's check the other one. At 1 and minus 2, d squared y upon dx squared is equal to 36 times 1 squared minus 48 times 1 plus 12. Hey, the second derivative is 0. What's my conclusion here? The second derivative test cannot, or does not allow us to determine the nature of this stationary point. That doesn't mean that you can't determine the nature of that stationary point. Well, I'm going to leave that for another tutorial, a separate tutorial. And the main reason why is the AdMath syllabus doesn't really test that concept. So I'm going to leave it for another tutorial. I'll still put it in the AdMath group, but it's good to know, and it's not difficult. All right, that's the end of this tutorial. And